Okay, so today we are looking at an application of rationals. You can see over here that there's a variable x in the denominator. That's what makes this a rational equation and application. Alongside it, we're also going to do a linear application. They're both considered variation, this topic of variation, when two variables vary or change as the other one changes. The direct one is linear. We could have done this way back in linears, but I decided to save both variations so you could see how similar they were. This one, that k acts as the slope, but k in this context is called the constant of variation. I have that written here. And the k here, still called the constant of variation, but this rational variable in the denominator, this linear. The one thing about direct variation is that it has to go through the slope. So if one variable is 0, the other one has to be 0. I already said it's linear, and the way this would be phrased is that y varies directly as x. So y varies directly as x means equals kx, and this one is y varies inversely as x, phrased in that manner. So it'll be pretty obvious what each word problem is. This first example, many areas of Northern California depend on the snowpack in the mountain range for their water supply. The volume of water produced from melting snow varies directly. So what varies directly? The volume of water varies directly as the volume of snow. So we could write an equation just to get this out. Water varies directly, so K times the volume of snow. So W for water, S for snow. So once you're given that, you're always going to be given some conditional, some exact condition that's going to allow you to find K. And then once we find K, K will remain the same throughout that problem. In this particular case, meteorologists have determined that 250 centimeters of snow, so that's our 250, will melt to 28 cubic centimeters of water. This is funny, given the snow day we had on Friday and the amount of snow I snowblowed this morning. So we're going to use this to solve for K. So we're going to divide both sides by 250. So 28 divided by 250 gives us 0.112 as our K value. Okay? Then we're going to use that K. So that pretty much writes our equation for us. So now the equation that's going to remain for the rest of this problem is W equals 0.112 S. That 0.112 is the constant of variation. So how much water does 1,200 cubic centimeters of melting snow? Again, that's a snow number. So we're just going to take 0.112, multiply it by 1,200 cubic centimeters, and 100 on your calculator. That's going to give you that the amount of water is 134.4 cubic centimeters. Okay. So as soon as it says direct variation, I write my equation, I start plugging in, I find K, I then use K with the given, question information, and then find the answer I'm looking for. The pressure in a can of spray paint varies inversely. So what? The pressure varies inversely, so K over, as the volume in the container, so K over V. The pressure in a container whose volume, so the volume is 8, and the pressure is 12 pounds. So we multiply both sides by 8, get K equals 96, and then that K is going to be our K for the rest of the problem. P equals 96 over V. That's the constant of variation linking pressure with volume. If the volume were 22 inches cubed, what is the pressure? So 96 divided by 22, and that's your answer. So So the pressure is 4.36. That 36 is repeating on my calculator. And then what's the unit on pressure? Pounds per square inch. Pounds per inches squared. I got that right from the problem. Okay, so you're going to have a worksheet for homework, which you probably don't have in your possession yet, but we're going to do number 25 from this worksheet. And here's the problem. If all men had identical body types, their weight would vary directly as the cube of their height. Very directly as the cube of their height. Shown below is Robert Wadlow, this giant man, who reached a record height of 8 feet 11 inches, which is 107 inches, before his death at age 22. If a man who is 5 feet 10 inches tall, 70 inches, with the same body type as Mr. Wadlow, weighs 170 pounds, what was Robert Wadlow's weight shortly before his death? So if I go back up into that problem, I have that the weight varies directly, so weight varies directly as the cube of their height. So look out for keywords. It's not just varying directly with the height, it's the cube, and not cubed root either. The cube means raise it to the third power. So we're going to, they do tell us Robert Wadlow's height, but they're going to eventually ask us for what Robert Wadlow's weight. So we don't know K yet. We're going to go to that next sentence, this if a man who is 70 inches tall, that's our H that we know, so 70 cubed, weighs 170 pounds. So the 70-inch man weighs 170 pounds. That's what we're going to solve to find K. 70 to the third power is 343,000. So if I divide both sides now by 343,000, I get K equals. My calculator shows me this. That's okay. That's scientific notation. 5 times 10 to the negative 4. I'm just going to keep that number on my calculator, but just so you can see, that's when you move the decimal place over 4 units. 1, 2, 3, 4. So it would be 0.0005 equals K. And then I'm going to use that K to find Robert Wadlow's weight. So going up here, now that I know K, his weight is going to equal our K value times his height cubed, 107 inches cubed. So 107 to the third power times 0.0005, and I get 612-ish, we'll round to near 10.5 pounds. Okay, so the key there is look out for varying directly with not just height, but height cubed or height squared or the cubed root of height. All is possible. Then we're going to jump to 30. The illumination provided by a car's headlight varies inversely as the square of the distance from the headlight. Okay, so there's our introductory statement. The illumination, we'll do I, varies inversely, so K over the square of the distance. So what you may or may not have noticed so far, but I'm going to point out to you, is that when it's inverse variation, as one variable goes up, the other one goes down. So for example, if the distance you're going to find here is, if the distance away from the headlight goes up, the illumination provided by the headlight is going to go down. In this particular case, we go on the details they're giving us. A car's headlight produces an illumination of 3.75 foot candles. That's obviously the unit for illumination. at a distance of 40 feet. So that's over 40 squared. We're going to solve this to find k. So 40 squared is 1,600. So I'm going to multiply both sides by 1,600 to get that to cancel. And then k will equal 6,000. So now using that k, I'm going to go up to my equation. I equals 6,000 over d squared. And I'm going to answer the question, what is the illumination? So we're looking for I, when the distance is 50 feet. So 6,000 divided by 50 squared. 2.4. And the unit, as we read, was foot candles. So your homework for tonight, as you see on the bottom there, is the worksheet that you're about to receive, number 1, number 3, and then numbers 21 through 30. Obviously, though, you do not need to do 25 again, and you don't need to do 30 again. So 21, 22, 23, 24, 26, 27, 28, and 29 you should do. 1 and 3 are just same type of problem, just not wrapped up in a word problem. So y varies directly as x for number 1. You're immediately going to use y equals kx. Y is 65 when x is 5, so plug those in. You can find k, and then once you know k, you can use that and the fact that x is 12 to find the y accordingly. And 3 is similar. So that's all for today. Hopefully I'm here tomorrow, and I'll see you then.